Of course. No, I wonder if he for me. Can anyone run to the postgrad office grab up Steve and the struggles? Well, you're the most athletic among us. Tell them they're all fired if they don't come. Do you want to enable your video camera, Alessio?
If you want, yeah. It's useful, I can.
Well, yeah. I don't know. If you want to be visible.
Well, I think the screen is fine. Should be enough. I can switch on after if there are some questions. Oh, yeah, they are. Okay. You tried to escape, huh?
No escape is not escape. All right, let me just make sure it is streaming. Yeah, it's streaming. All right. All right. So welcome to this extraordinary colloquium.
Let's see.
Very glad to have another one with a very dignified visiting speaker. So our speaker today is Alessio Trafficante. He might sound exotic, but actually he is a rat as well, because he is, as of a couple of months ago, he is an honorary research associate at Rhodes. And as you probably know, he is Steve's co-supervisor. So he really is one of us. But originally, of course, he is from Rome. I believe he got his PhD at the University of Rome in 2011.
Yeah.
Working on Herschel data. And since then, he's had a number of postdocs in Rome, with some stints at Caltech and Manchester, but mostly in Rome. So he clearly likes Rome. Fortunately for us, he also likes Rhodes. So he's worked quite a lot with ALMA, and now he's a researcher at INAF in Rome. He is the lead scientist for the Meerkat 5 Band 5B receiver, and for the surveys that are going to be done with it. And he's going to be talking about a subject that, as radio astronomers, we don't hear of too often, right? He's going to be talking about stars and stars formation. So I think this should be very interesting for us. For the remote participants, if you've got questions, please put them in the Zoom chat, and we'll ask them after the talk. Otherwise, Alessio, over to you.
Okay. Thank you, Oleg. Thanks a lot for the nice introduction, and thank you all for the invitation, in which is my second university at this point with my honorary appointment. So, as Oleg said, this is a topic that you don't hear often here, but I think is super interesting also for people working with Meerkat, as we will see a bit later, very quick. And I want to give you then an overview in a much kind of broader way to give you an idea of what's the topic that is behind the star formation, which is the main topic of my research. So let's start from a very basic question and discussion, which is about the so-called IMF, so the initial mass function. So basically what we want to understand is what's the distribution of the stars that we see in our galaxy, from the low mass ones to the high mass ones.
Sorry, Alessio, are you sharing the screen on Zoom?
I am, I guess.
Because what I'm seeing on the live stream is this.
Then let me share again. Okay. Let me back to the presentation mode. How about now?
No.
Is the wrong one? How about now? But then it goes up here. The usual problem. Give me a second, huh? Sorry about that. That's what I have to do. Let me switch again. Oh. is this changes? Okay. How about now? Okay, so should work. Okay, perfect. Okay, sorry about that. So what I was saying is we want to understand this distribution of stars because they are critical for shaping our galaxy and any other galaxies, of course. Now, it has been long thought that this distribution of stars is a sort of universal, in the sense that you have this log normal distribution of the mass of stars with different kind of formula depending from the models and observations in the low mass part, but the high mass tail is always with a very typical power law, with a power of 1.35 to 0.35, depending which kind of space you want to use. This typical power law has been long considered universal and is critical because it means that we always have the same amount of massive stars given the amount of low mass stars. Therefore, the kind of kinematics of reshaping of the galaxy that you can imagine of can be predicted as long as you count the number of low mass stars in the galaxy. Is this true? Of course, never is that easy. So, especially if you start to move in very massive regions, things change. And you can start to see that's an example. It's not super clear from the plot, but if you look at the numbers, the best fitting IMF here has a slope which is we call top heavy. So an excess of high mass stars are found within the regions that are the most massive in the galaxy, meaning that the most massive regions in the galaxy not just shape their own regions, but they also reshape the entire galaxy with this excess of massive stars. So is this universal or not? If you want to understand what's happening in these extreme massive regions, we have to understand how we form high mass stars in massive regions. And this will be the topic of my lecture today. So basically understanding the high mass star forming regions, so trying to understand that. To do that, we will pass towards a few steps. So first, I will review how we organize, let's say, the different structures in the galaxy. And then, if it works, then once we reach the parsec-scale structures, how inside we start to form the cores, which are the progenitor of the final stars. And now we can then define the core mass function, so the equivalent of the initial mass function, but for these core objects. How it evolves and changes, and what will be the role of ALMA and MeerKAT and in future SKA to understand this kind of topic, and then what we will learn also from the simulations. So let's go into the business in a bit more details. How does massive stars form? So they start forming from what we call giant molecular clouds. So those are objects that are distributed in the galaxy up to 150 parsec long, with a relatively shallow density compared to the rest of the star forming side. Inside is the giant molecular clouds, you can create the giant galactic filaments, or even small galactic filaments, up to 100 parsec, and of course smaller than that. Inside those filaments, you start to create the real progenitors of the stars, and the mass stars in particular. The object that we call clump. Those are roundish objects of about a parsec scale in diameter, and those clumps may then fragment in what I was anticipating before we call chords, fragments, but let's call them chords. Now the radius is between 1,000 and 3,000 AU or so, and the mass goes from 1 to 10 solar masses, depends on the object, or even more. And all this process is regulated basically by different factors. The main ones are gravity, turbulence, and feedback. The interplay between them will regulate the formation of your object. Of course, the gravity pulls towards the formation and the fragmentation of your cores. Turbulence and feedback may actually act double way. Turbulence may accumulate mass towards the edges, but may also sustain the gravity against the collapse. And feedback the same, can actually act against the collapse. For example, if your feedback comes from a very ionized region like H2 region, the one that we can study with MeerKAT actually, but they can also trigger star formation at the edges of this ionized region. This interplay is the key to understand which is the main actor. Is it gravity, is it turbulence? If you change those actors, you change the rate of formation, and then you change the amount of high mass stars that you can find. Yes?
Could you drop the zoom bar?
Maybe I can. I think I can. Okay, sorry about that. Okay. Okay, fair. So the goal here is to understand this interplay and the implication of this interplay at the various scales to understand how we finally form these massive stars. Now, there are several different mechanisms, but I want to go in the simplest one, and actually one of the most used to understand that, which is the turbulent cascade. We know that if we have a turbulent cascade, we expect the energy moving from large scales down to small scales with a sort of constant power law, and that can be measured in the interstellar medium. And in particular, you can measure for your medium your velocity dispersion of your gas, the radius of your region that you are looking at, molecular clouds, filaments, of course, whatever, and you can build a relation between the velocity dispersion and the radius. Now, if your medium is supersonic and turbulent, as you would expect if turbulence is dominating, there is a clear relation between velocity dispersion and radius, which goes like this. The velocity dispersion is proportional to the radius of the power of 1.5. This is typical of the Burger turbulence, so supersonic turbulence, and it's also the relation that has been found by Larson in 1921. Mass and surface density will also come into the game, you can see that later, because of course, if you have higher density, higher mass, you would expect the gravity starts to play a game. That will change this law. We will not go into these details, just to let you know that, of course, everything is never that simple. This is a very simple law. Nevertheless, it would be nice. Okay, let's go back to it. Nevertheless, if you plot this very simple law, measure the scales of your giant molecular clouds, you see a very kind of nice relation, especially the scales of the giant molecular cloud. This is an example of old work done in that using the 12CO120, so a tracer of relatively low density material, and you see that the law scales very well with this power. That's where we assessed for 50 years now, more or less, that the molecular clouds are basically dominated by turbulence. What happens anyway if you want to move inside your molecular clouds? So for example, you want to start to look at filaments. Then you need a higher density tracer. So your CO120 start to become optically thick. So you cannot trace anymore the velocity dispersion of your gas. You have to go to different transition, different isotopes of your CO, and you get a relation like this. Now, if you want, we still see a sort of Larson relation, but you start to see a lot of dispersion. This is very interesting because meaning that as you go inside, it's not simply turbulence. Something else may happen which start to dominate your collapse, which means that you cannot simply using the model that describes turbulence as main mechanism to form IMA stars to justify your final IMF. So the next obvious question is what's happening inside when we start to accumulate material and form these dense clumps. First, how can we observe these dense clumps? So as I said, just a summary, at a large scale, we have in relatively low density environments, we have something that resembles a Larson turbulent relation. Let's look at the clumps, but first, how we identify clumps? So since you're not used to work with satellites like Herschel, I think the best way for you to understand how complex is the turbulent gas and the graviturbulent gas in the galaxy is to look at what Herschel has seen in the past. So Herschel is a satellite that have looked at the far infrared emission from 70 micron to 500 micron, all the entire galactic plane. Now, this is the emission where the cold dust associated with subforming regions is peaking. And if you look, that's an image of a piece of the galaxy has been seen by Herschel. The 70 micron gas is the warmer, 50K or so, and is where you can spot these subforming clumps. The rest are all a plethora of filaments, which are colder and can be seen at 160 and 250 microns. But as you can see, this is the galactic center. It's a very complex interplay of filaments, clumps, and structures. So identifying all of them, extracting their properties, and trying to understand how the formation works is not an easy job at all. But I think it's very instructive to see what has been done in the last 15 years with Herschel. Now, next step for us is to extract the clumps in here. So, as I mentioned, the clumps are those kind of roundish objects, which have a size of about a parsec. And since now we have 5 wavelengths in Herschel, we can do a very important next step to understand how those things work. We can classify them based on their evolutionary status. So if a 70 micron object is bright or dark, this will change a lot because at the beginning you have a very cold dense gas that accumulates. A very cold dense gas will not emit at 70 micron because 70 micron is a wavelength that starts to be switched on when your temperature increases above 30K. So you can have clumps that are very well seen at 250 micron, so a cold dense gas, but they're completely dark at 70 micron. Very early evolutionary stages, we call them starless or prestellar objects. Vice versa, you can have objects already switched on at 70 micron, and then you move into the protostellar objects, where the protostars start to warm up your envelope. The next step of this for the massive regions is the formation of H2 regions, which start to ionize your medium, creates feedback, and makes things much more complex. You can see also that in terms of temperature, from the quiescent prestellar phase to the H2 region, you have a clear increase in temperature. Why we want to look at the evolution of those objects, we'll see a bit later, but the point is here, do we see the Larson relation of these clumps, which start to be broken already at the filament scales at all evolutionary stages of the clumps? Now, how many clumps do we have in the galaxy first? So from the plot that you have seen before, we have extracted all the objects that have been seen in different wavelengths, and we built the evolutionary physics of this clump. This was a huge effort in the past. We built about 200,000 sources in the galactic plane. So quite a lot to have a good statistics. And as you can see, they are distributed all over the galaxy. This is where our solar system is. This is the galactic center. Given the distance of this object is extremely complex, so take it with gram Musalis, but that's more or less the idea. Now we want to look at the kinematics. We need the velocity dispersion of these objects. We can extract the radius and the rotary formation from Herschel, but we cannot extract the kinematics from Herschel, which was just a dust continuum. We need lines. So what we did in the past was to look for a line that was able to trace these extremely high density environments, which is the N2H plus 1 to 0. So those 3 millimeter lines are super useful to look at these guys. These are relatively faint lines compared to the CO. So you need to integrate it for quite a lot of time. And actually, this is yet to date the largest sample of clumps traced also with N2H plus 1 to 0. And if you combine the Hi-GAL with this large survey of N2H plus lines, you get 213 clumps. So statistically speaking, not comparable to 200,000, but still the largest sample we can have nowadays to look at this kind of dynamics. Which means that for these 200 clumps, we can build the radius, the velocity dispersion, therefore the Larson relation. And how does it look like? It looks like this, which, despite what you can imagine, is very informative, because there is no correlation at all. And that's for the different phases of evolution. We try to classify them for different phases, even a bit more complex than just starless and protostar and H2 regions. But as you can see, if you put all together, or if you simply divide them for different phases, you don't have any correlation. That's extremely informative, because it means that at these scales, you would expect that your turbulent cascade is broken, and some other mechanisms start to dominate your velocity dispersion, which must be gravity at this point, because those guys are supermassive. That would be the implication. Do we see this all over the place? So, as a small summary, if you look at the cloud scales, so above a parsec, you have a sort of Larson relation. Once you move below 1 parsec, gravity may start to pull and give you an excess of velocity dispersion with respect to what you would expect from the turbulent cascade. So you may have a break of this turbulent cascade at around a parsec scale. Is it true that we have a break? The answer is yes. So we did this exercise a couple of years ago now. We took some regions of sun-forming regions. We look at both the velocity dispersion and the radius at the cloud scales here, and inside, below the parsec scale here. So the purple points here are taken with N2H plus. Here we got the CO. So the same game that we did before for random regions, we try to do for the same regions. You can see that there is quite a confusion here, which some sort of resembles the Larson relation, but there is definitely a flat velocity dispersion below the parsec scale. This flatness is a clear indication that cannot be a turbulent cascade only regulating the system below the parsec scale. This has been seen in other works. Here are some plots of what you would expect from, let's say, look at the scales from molecular clouds down to clumps and cores. Here is slightly more evident. Here is much more evident. Those are a combination of several simulations done to replicate the formation of stars from galaxy scales to core scales. and you can see how you have a sort of Larson relation on the large scales, so turbulence dominated, and this break which is around the parsec scale below. Now, as you can see, this break is more or less around the parsec scale, not exactly at parsec scale. So the question is a break due to the size? What we wanted to interpret in this sense is that the break is more or less around these sides, but this size is also critical in terms of density of material. So the break must be done not just for the scale, but for the density that you reach. Above a given density threshold, you would expect that your gravity starts to dominate over the turbulence. So we came out with this model a few years ago, in which basically the idea is when you have low surface density, so high scales, turbulence is dominating, then you have this interplay, and then you end up with a very simple model in which gravity will dominate above this threshold, which is equivalent to stay above more or less a parsec scale. Now, this is nice, this is okay, but what's the implication of all of this to the formation of the excess of IMA stars for the distribution of our final IMF? So the next step, now that we understood that at the parsec scale for IMA stars, we expect the formation of a gravity-dominated field, what's happening inside those clumps? Now, the theory told us that there are two possibilities. Either you have the so-called core-fed model, so regardless of the fact that your gravity is pulling down material in your clump, the pressure around the formation of your cores isolates your cores. So it will form a sort of isolated, high-mass starless core at the beginning that then will grow up and form your protostar. This has a totally different outcome in terms of model and expected IMA stars with respect to the clump-fed scenario. In the clump-fed scenario, these dynamics of the gravitational pull into the clump will keep forming with time more and more cores, which actually are created with time. This accretion is dependent from the mass of the original clumps, and they keep accreting as well with time in a very dynamical fashion. This different approach, of course, will lead to a completely different distribution of cores, which may also evolve with time, and this is critical. We will see later what I mean. So in the past, we had to look at these fragments and cores with very high resolution, so we need ALMA. We did some survey of ALMA with small samples, as you can see here. All those plots have the mass of the clump on the x-axis, the mass of the cores on the y-axis, and you can see that all of them have a sort of distribution that suggests that the mass of the cores increase with the mass of the clump. Again, you will never find a very nice correlation in these things because there are a lot of parameters to take care of. But let's say also statistics is very low because those require hours of integration time in ALMA, so not something obvious to obtain. But you get an indication that seems to go in this direction. Things may change if we start to look in a statistically much more significant sample. To do that, we have to move to ALMA again, but to large surveys. There are two large surveys that have been designed to look at ALMA for this specific topic. Let me start with ALMAGAL. This is the largest survey of fragmentation onto clumps that we have now in our galaxy. We observed more than 1,000 clumps. It took about 100 hours with the most extended array to 1,000 AU resolution. This is the distribution of the clumps. You can see that they are distributed also for different surface densities, just to understand again if the interplay of this turbulence and gravity in different regions, we have different outcome, some selection criteria. We just ended up last year with the first catalog of fragmentation of cores. You can see here an image of how those clumps look like in ALMA. And there is a very different distribution of cores. I will not go into the details. The point is that we got more than 6,000 cores to work with. So different statistics with respect to the 100 we had before. Just to give you an idea of how transformational this project is compared to the others, this is the number of clumps that has been observed in all the surveys that have been dedicated to these works, compared to the number of cores identified, and you see that we are an order of magnitude above with ALMAGAL with respect to the other surveys done so far. And so is the L over M, which is a typical indicator of the evolution of the clumps. So the one that I was using to divide between prestellar, protostellar, and H2, you see that ALMAGAL will cover all the evolutionary phases. So we can have really all that we need to understand this distribution. What do we learn? We learned something like this, which I think is extremely interesting in this topic. So L over M, again, an indication of the evolution of your clumps. versus the mass of the core. The red line, let's focus on this now, is the mass of the most massive core that you find in each of these clumps. And as you can see, this is relatively good statistics in this sense. The mass of your cores with time of your massive cores tend to increase. That's a very clear sign of clump-fed mechanism. You clearly can see now that when you start to form your clump, they start to fragment in many small cores, but the bigger ones start to increase and increase with time. So there is this increasing of material, which in theory is supposed to be gravity/feedback driven, that goes through this clump-fed mechanism. The blue line is actually the mass of the least massive core, which is extremely indicative as well. That means that even with the time of evolution, as you move forward, everything is connected and you keep forming new small mass cores across your clump. And this is, well, this also goes in this same direction. This is the number of cores that you find as a function of the most massive core, so in a way of your evolution. So you keep forming more cores as you move with time. But this is not the central point. The central point, I think, is this plot here that really points toward the idea of this core evolution. Now, if we have core evolution, what's the impact on the initial mass function? Because if those cores keeps growing, the initial mass function, so the final formation of stars, may be related to the final stage of our core mass function, if our core mass function also increases with time. Let's see. Before looking at that, let's introduce the other ALMA large survey that, as you can see from the name, ALMA-IMF, has been designed exactly to understand the connection between the ALMA cores and the IMF in the galaxy. What they have done was basically to build select 15 high mass regions across the galaxy and to look at the fragmentation inside. So while with ALMAGAL we were looking at 1,000 clumps, so parsec-scale structures all over the galaxy, they focused on an entire region, 15 of them, to look at the fragmentation within the same regions. And with that, they were able to select about 600 cores and then to build what we called the core mass function. So now we have statistically significant samples of cores. We can look at the same, let's say, the progenitor of the IMF, but of the core. So the so-called core mass function, and now actually it evolves with time, if it evolves with time. So what do we learn from ALMA-IMF? This is the results from a couple of years ago. It's the global core mass function of all the 50 regions they found. Now, this is a bit controversial to me, but let's go to what they claim in this result. So the red line is the classical power law from Salpeter. They claim that the best fit of the distribution, which are the gray lines, is the blue one, and so it's slightly top heavy. So you have an excess of high mass stars forming in those cores. I think we can discuss this result quite a lot, but I think the next one is a bit more robust. So just to give you an idea of what they have done, this is a single region, W33. This is the region that they've seen with ALMA. You can see here a number of cores. And so they built again this core mass distribution. This is the Salpeter slope. And what they find for the global distribution of the core mass function is that it's basically comparable with the Salpeter, or slightly actually steeper. But very interesting is these results. Now we can classify the cores for evolutionary stages. What happens if we build the same by separating the protostar from the prestellar, so the young cores from the more evolved cores? You can see that the prestellar is much steeper than the protostellar. That means that you have a clear evolution of your core mass function with time. So that can really pinpoint towards the fact that you have an excess of high mass stars in your IMF in massive regions with time, because your CMF starts as a Salpeter-like, so with this slope, and if you are in a very massive region, so due to the pull of gravity, this will start to increase your cores, and therefore to form, at the end of the day, more high mass stars. This is actually confirmed very well by ALMAGAL. So we did the same with ALMAGAL. We have 6,000 cores here, and here is the CMF, regardless of the value of the K exponent, but look just at the yellow and the blue distribution. The yellow distribution is the CMF. You see those distributions because the temperature of these cores is not easy to fix, and the temperature will determine your mass. So we did a sort of Monte Carlo random distribution of temperature to get an idea of what we may expect. The yellow distribution is the core mass function for very young clumps. The blue ones is for more evolved clumps. As I showed you before, we have this increase in core mass, and this actually pinpoint in the same direction. You clearly have an increasing of your core mass function with time. This is extremely valuable as a result because it really points towards the idea, as I said before, that we can now justify why in some regions, in massive regions, we find an IMF which is not canonical. Very likely because there is this growth mass already at the core stage. This is everything that has been done so far in our galaxy. Now, the next step that we tried to do was, and we asked this, okay, what happens if we want to look to an external galaxy? This is extremely challenging because, I mean, our galaxy is here, external galaxies are not here, so you need to push ALMA quite a lot in terms of sensitivity and resolution. But this is the distribution we had so far of this core mass function seen at a resolution of 0.1 parsec, the best that we could have. And this is the IMF I showed you at the beginning, where we have this top-heavy excess of IMA stars. Now, this distribution seems to be salpeter-like, so there is not a correlation between this distribution of 0.1 parsec and the IMF you see in the nearest galaxy we can think of, so the Large Magellanic Cloud. In particular, into the 30 Doradus region. This is the very famous bright region where you have the Tarantula Nebula or the very famous ionized region in the galaxy. Now, what we tried to do was to push this a bit further. This is an image of these 30 Dorado regions. R136 is the Tarantula Nebula. And this is an image taken with a JWST of the ionized emission. This is spatial alpha emission line, which traces the ionized gas. As you see, it's a very complex ionized region. And this is what we had to build this CMF. So the 0.1 parsec region seen with ALMA already pushed quite a lot. What we tried to do, and we were successful, was to push ALMA at extremely high resolution. And we tried to look at these guys down to 2000 AU. You see that what before was just one core, now fragments in two big clusters with a lot of cores inside of them. In total, we have 4 of these protoclusters, which reached a total of 71 cores, which we could then build the first core mass function outside our galaxy to see if in a different complete context, in this case, the metallicity is much lower than our galaxy, but not lower where it's lower in our galaxy, which is at the external part of the galaxy, but it's lower inside the most active regions of the galaxy. And what happens if we build the CMF here? As I told you, we have this top-heavy IMF, we have a salpeter-like 0.1 parsec. This is the distribution that we get. Again, we cannot give a single number because we cannot trust the mass estimation because of temperature estimation, but we can do a lot of Monte Carlo analysis, and you can get a distribution of exponents like this, and you see this green line here is salpeter. This is coherent with a salpeter-like, actually slightly top-heavy, which suggests that since we also know from the JWST data that this region is actually relatively young, that it's very likely that also in external galaxy, the same physics that we imagine working in our galaxy are working. So we basically have an evolution of the CMF also in this galaxy, and what we are looking at here is a relatively young stage of the formation. So these results are now going to be published soon in Nature Communications, so I ask you not to take picture because it's still under embargo, but I think it's very nice to show. So just to summarize what we have discussed so far. What drives the star formation flow? As I mentioned, we have these cloud scales, clump scales, core scales, and interplay between gravity, turbulence, and feedback. Now, if you notice, I mentioned the Larson relation at the clump scales. I mentioned the Larson relation at the cloud scales. I didn't mention yet anything in terms of correlation between clumps and cores and kinematics between clumps and cores. This is because we didn't yet have a statistically significant sample of objects for which we have information of the kinematics from clump to core scales yet. Because we got this ALMA large project just last year, we are acquiring the data right now. This is an extremely valuable project for this kind of topic. So basically what we have done was to select a sample of 206-ish clumps for which we have information on the large scales from the CO and all the small scales from ALMAGAL. So the missing piece was really to look at the clump to core scales with all the lines, like in 2H+ that I mentioned before, to get all the information that we need in terms of kinematics and dynamics. So this will be a huge effort for the years to come to understand finally the gas kinematics from clumps to quartz on a statistically significant sample and on different evolutionary phases of the cloud. This should really give us the answer to understand the physics that is behind the evolution of the CMF that we have measured so far. Is this enough? Of course not, because we have the feedback. Feedback may really change the game. Feedback means that you have some sort of, in this case, in this example, a ionized emission that may push towards everything that gravity is pulling on, or turbulence is also playing in the game. One of the biggest, let's say, sorts of feedback are the formation of these H2 regions, which start from a very small one and hypercompact objects. Those are the parameters. I don't want to go into the details. Just know that we know about 20 of them by serendipitous discovery, because they are very small and very faint, so not easy to catch. Then you evolve from hypercompact to ultracompact H2 regions, and then to the final H2 regions that you can imagine, this big bubble of ionized gas. How can we look at this emission? This is free emission. Free emission is traced very well by radio emission. And that's where MeerKAT will come into the game. So MeerKAT is what we are using to trace this radio emission, to trace these H2 regions. And in particular, since the spectra peak just around 1 to 20 gigahertz, MeerKAT is really perfect also to see the evolution of the spectra, and in particular to get also the smallest one. So here is a plot of the distribution. This is the emission. Don't look at the y-axis, just look at the x-axis. Those are the size of the ultra-compact and the transition to the hyper-compact in logarithm. As you can see in blue here is what MeerKAT could have done so far to look at these objects up to 10 kiloparsec away from us, so basically covering the whole galactic plane at 1.3 gigahertz. Now, as you know, we have the 3.1 gigahertz in the free continuum that we can use, and the combination of those two will allow us to look at, for the first time in details, actually at the transition between ultracompact and hypercompact for some of the regions in our galaxy. As soon as we will have MeerKAT in band 5B, so 10 to 15 gigahertz, this will be really a game changer. We can build the full spectral energy distribution of these radio objects, and we can start to cover down to the hypercompact H2 regions. Look again, these are taken at 10 kiloparsec. As soon as you move to 5 kiloparsec, which most of the massive regions are, we basically can cover almost all the hypercompact H2 regions. Of course, if you really want to do this job properly, SKA will be the final answer. With the resolution that we can get and the sensitivity that we can get, we can really understand the formation of all the new hypercompact H2 regions across all our galaxies. At that point, we should be able to really understand how the feedback is impacting the formation and the interplay of gravity and turbulence. What we started to do, as Steve knows very well, is to look at one region which is very rich in terms of star formation. Here is a 1.3 gigahertz image of this region of the galactic plane. You can see how bright are some of those regions. The red circles here are all the ALMAGAL and Panta-ray sources that we have. So for these regions, we have 480 sources, all the information in terms of kinematics, dynamics, and outflows at the position of these 80 ALMAGAL sources, which are in different evolutionary phases. So for the first time, combining with MeerKAT, as soon as Steve will go into that, we can really look at the combination of feedback, gravity, and turbulence across this specific region. So this will be the first answer to the question of how the physics will change the morphology of the CMF. Is that enough? No. Again, I would say, well, observationally speaking, yes, but we are also trying to look on a different side, which is the simulation side. If you really want to understand what's going on, you need to combine all those information with models. And you cannot simply produce a model of a galaxy formation or a clump formation if you want to compare directly with observations. What we were trying to do with this project that we call the Rosetta Stone, which was done because we really want to compare, to have a language, let's say, to compare observations and simulations. So we started with a suite of simulations. Here is an example. Then we post-process them at the specific wavelength that we would observe with a given telescope. And even more importantly, we then post-process them even more to really have the simulations at the same level of observations with the same kind of observable bias that we have in observations, to see if the information that we get from observations can be really retrieved in the simulations. And knowing the physics that is behind the simulations, we can understand if our interpretation of observations is correct or not. I will not go into the details of all this work, But just to let you know that what we tried to do as the first step was to build a suite of simulations that will try to replicate properties of the clumps that we know, like mass radius, and properties that we do not know, like the intensity of the magnetic fields or the level of turbulence. Combining all this set of simulations, so we got a suite of more than 700 simulations at different evolutionary stages, and we can really compare one-to-one each of them with our clump to understand what's the physics that generated that particular fragmentation. That's just to give you an example, that you can really simulate all the different processes that happens in our case in ALMA, because we wanted to replicate the ALMA data. And now, from the simulations you can start, you can use the basic ALMA model, or you can use our pipeline, and you see how closer to the real observations we go with this new pipeline that really takes into account every details of the observations. Now, this was a huge effort, as I mentioned. I don't want to go too much into the details. Just to give you that in gray here, you have the distribution of the Rosetta Stone simulations. This is evolution versus basically mass of your cores. And you see that the increases as you would expect in these global mechanisms. So we are able to reproduce and to observe through these simulated observations what we see in the real observations. Next, of course, is now to build a synthetic CMF and to see if we see the evolution of it as we see in the observations. Let me conclude quickly with the next step that we are going to take, because I think this Rosetta Stone framework is extremely powerful to understand different kinds of physics. We are now going down to the resolution of ALMAGAL, so we can really look at more than 700 simulations as if they were ALMAGAL clumps. You can see from this number of fragments, in blue here is the new simulations of the ALMAGAL scale, so we can really improve the number of cores we can extract and really do one-to-one comparison. And even more interesting, I think, is the next two steps. One is that we are now post-processing those simulations using a code that is able to replicate the impact of the magnetic fields, the orientation, the intensity. So while the orientation can be somehow observed, the intensity is much more complex. But now with this post-processing approach, we can really see how we should observe the intensity and the orientation of the magnetic fields in a given Stanford region. Even more interesting for the work that you do around here, guys. Now we have added one module into this framework to also simulate the post-processing of the free continuum emission. Here you see in purple a distribution of free emission from a simulated H2 regions. We were able to simulate the electron density and to post-process it to a radial transfer approach, which gives us exactly the intensity that we should obtain if we look at it at 10 to 15 gigahertz, which are the basically the frequency of the band 5 data, both in MIRCAT and SKA. Next step, we post-process it assuming the distribution of dishes of the 15 gigahertz SKA dishes. And this is exactly how we would expect this region would be seen by SKA once we will have the 15 gigahertz receiver installed on board. With this, we can really predict what SKA should be able to do. So I will conclude here. I will not go into the details. What I will just say is that we are on the verge of understanding the physics that generates the core mass function and the distribution of cores we observe. And even more importantly, we are now starting to have large projects and frameworks that can allow us to really combine all these efforts into one big project. So looking at all the observations and the evolution of the cores, the core mass function, interpreting them with the simulations to the Rosetta Stone pipeline. And with that, I will conclude. Thank you.
Thank you very much, Alessio. We've got time for questions, and remote people, if you can raise hands or post questions in chat. What is the question?
Thank you very much for the great answers. Yeah. Are there any cases where a collapsed cloud doesn't necessarily go on into stars?
Yes. Oh, actually, there are all the cases that we have a big molecular cloud with different clump kind of region, and not all of them will form stars. So some of them will be transient. And it's very difficult to distinguish between a transient clump or a transient cloud, if you want, and a real one, because as you can imagine, once you observe the galaxy, we have one snapshot in time. So that's why where a Rosetta Stone kind of simulations can help, because observationally speaking, the properties of transient clump and actually a real clump that is collapsing are very difficult to distinguish. So yes, we have cases, but only simulations can help us to understand which one is which.
And you don't know basically what kind of physics would, prevent a collapse of clump from eventually.
Let's say, in principle, is turbulence on the large scale, but you have to look at the environment. It may be possible that you have a supernova explosion just right in the angle, and if we don't match to understand what's happening in the environment, we cannot know why in that specific case it's not happening. We still didn't yet, I mean, all the 1,000 clumps that I showed of ALMAGAL, we didn't yet try to put them in the context of the environment. So we don't know if, for example, the ones that are not producing any fragment, because some of them are not fragmenting, are because they are in a region that by chance is just a transient region and is being destroyed in the next step, time step, or if there is something else. We are still not yet there. So good question. If some of you are interested in doing this job, guys, we have a lot of data to work and a lot of other questions.
I'm quite interested in the simulation aspect of things. So, there was an R in your MHD. What does the R stand for? Simulations.
Yeah. Let me see, where do you find the heart? So I can tell you.
R in
yes, radiative transfer imaging.
So are these the parameters that you play with? I mean, like you have to specify some kind of equation of state.
Yes.
And what do you?
Is the typical equation of state. So it's the continuity equation and the initial equation of state. I need to check the paper for the details. The simulations have been run by Hugo Lebris from France. I cannot not tell you exactly now the details, but they are in the paper. I can tell you which equation of state has been used. Yes. So basically, you start with a sphere with some initial level of turbulence. You drive the turbulence for about 2 crossing times before you start to switch on the gravity, and then you let the clump collapse.
So, I mean, you said that you've got the a mechanism of turning these images into visibilities for specific telescopes. I mean, that would be incredibly valuable. For example, train noises and stuff. For imaging. You know if there's people using that data for that?
Not yet. We are in contact with actually, we done that specifically for ALMA now, but as I showed you here, we have done a bit with SKA as well. So we are in touch with the ALMA people to try to see if this kind of process and framework can be introduced into the simulator. It would be nice actually to add this also into the SKA or MIRCAT simulator. I mean, all this part of the work, this post-processing part has been done.
If you give me the images, I can build the simulator.
Yeah.
So this is the product that gets produced.
This is the actual product, yes, from ALMA. For specific.
No, I mean from the Rosetta Stone simulations.
Yes. So this is the column density that you get from the simulations.
Yeah. So if I can get my hands on that, that would be very useful.
Of course, we can talk later. As I was saying, this last step has been done by my PhD student Alicia in Rome. So she knows all the details of how she converted them into visibility. So we can talk after.
These are full Stokes maps that you're looking.
Yes.
But
let's talk later.
While on Ramses, something just came to mind. Are these stars allowed to collapse? These particles, are they allowed to collapse? I don't know whether Ramses treats
Yes, so the stars here are the sync particles. Yeah. So basically, once you reach the resolution element, you go in sync, and they are not allowed to merge the sync. But the sync here at the scale below 30 AU, so very small scale. What we are assuming here in this very high resolution simulations is that one sync is one star and cannot merge with other syncs. It's not super accurate, but merging syncs, it's very computationally expensive. So
I imagine if I'm in a global cluster, then collisions.
There should be, well, I mean, we simulated those collisions above 30 AU. So cores before forming sinks can, of course, merge. But once you form a sink, you assume that is a sink. Yes. That's another step. But I mean, there are two directions we are trying to get. Well, the main direction we are trying to get is to get the environment for what we were discussing before. So larger box to see what's happening around. And if you go for a larger box, you cannot increase your resolution. Otherwise, you need really the computational time forever. And so we cannot go into the merging of the sinks if you go for larger boxes. Compromises as usual with simulations.
Any more questions? I had a question when you said you like that result, that's the result from electrical communications, which we are absolutely not supposed to take pictures of.
Of course.
For
another week.
For another week. You said you really pushed ALMA. Pushed it in which sense? What was the?
The configuration is what we call 314.8. So the resolution was 0.05 arc seconds, 0.04 actually, and integration time was about a couple of hours per pointing, which is for our kind of science pushing ALMA quite a lot down. And the point is that we couldn't know if that was enough to observe the fragments that we see. Because I mean, we did some calculations based on what we observe in our galaxy, which was the only thing that was available. But that we could have seen this, nobody would have predicted that. We were lucky in a way.
I also have an image,
Okay.
but not of that reason.
How deep is it? Do you remember?
Okay, check it.
Yeah, we can see that later as well.
Okay. Last chance for remote questions. I don't see any hands. I don't see any questions. Any more questions in the room? Okay, let's take Alessio again.